This paper was published in 2018 by OpenAI, by Alec Radford and other authors, in a collaboration from Google and also the University of Toronto. The title of the paper is on Improving Language Understanding by Generative Pre-training. I was personally motivated to talk about this paper because it introduces a novel approach to handle language understanding. And I was also very interested on a personal note because I worked with conversational AI a couple months ago as a developer or as a software engineer. So this is how I divided my presentation. I will briefly talk about the area of natural language processing and give a foundation for the experiments of this paper. And I will talk about, in the second place, about the setup of their experiment and the results. And lastly, a brief conclusion about it. For starters, let's talk about the current scenario of natural language processing. And every year on August, the Gardner Institute releases a hype cycle for emerging technologies chart, where they list a couple trending technologies that if you look at the left side, you will be able to see technologies that are in the innovation trigger. So technologies that are still experiencing innovations. They are still undergoing innovations and they're still experiencing new discoveries. And on that note, conversational AI platforms and artificial general intelligence, they are set to be, or they are predicted to be, within the next 10 or plus years to still be a very relevant technology, and that it will reach its plateau that you will be able to see on the right column of the chart. It will be able to reach the plateau and on average of 10 plus years. So it is still a novel technology and it is still experiencing a lot of innovation and growth. And that's why I become very interested about this research as well. So NLP is a very broad subject. It comprises different tasks such as textual entailment, question answering, semantic similarity assessment, document classification, and many other tasks. And in this field, although we can find a lot of unlabeled data, for example, we can look at texts, we can look at books, we can look at how people talk and get data from that. We can look at just common phrases. So in terms of unlabeled data, there's a plethora of data available out there for people to use it, although there's a scarcity when it comes to labeled data that trained models or by machine learning can use to accurately or to predict adequately in this industry, right? And thus, the ability from a model to learn from raw text or unlabeled data is crucial in natural language processing. I would like to give a 90-second walkthrough a application that app that I have developed for iOS. And this application comprises technology such as Google text-to-speech that uses the WaveNet technology recently published or made available to the public. It also uses speech recognition. On top of that, it's using Rasa technology to perform a natural language understanding and also PyTorch to build the model to do the predictive algorithm. So this app is a conversational AI application where you can get to talk to an AI machine and interact on a voice base. So let's give it a quick walkthrough presentation about it. Oops, and there you go.
Hi, Hi, let's reflect your day with me this evening. How happy do you feel right now?
Very happy, thanks for asking.
Understand. How energetic are you right now?
Not so much.
Dream big and dare to fail. Let us start with tracking your habits. A lot on your list today. We have waking up early, use the Rocky app, my first habit, do push-ups and running. Are we done with waking up early yesterday?
Yes.
You did well yesterday. Keep on going. When did you start dreaming the night before?
What are you talking about?
How did you use your extended morning time?
I don't know. What are you talking about?
Would you like to store additional notes for this habit?
So at this very point, I deliberately quit the conversation because the predictive model that generates the conversation for the AI wasn't being able to recognize my confusion about the question that it was asking. Another limitation of this application is that when I ask the question, what are you talking about? The speech recognition from Google did not recognize my what I said as a question, but rather it just processed the information as just as a text. So that can also be seen as a limitation. And another limitation is that in conversational AI, it's very difficult for you to be broad in terms of to build one single unit model that can be applied to different areas or different subjects and have the algorithm or the model to be able to handle different contexts of conversations. So at this stage of the app, the users are allowed to give a score or give a rate for the overall experience talking to the AI bot. And based off of these scores, the predictive model gets updated to enhance the accurability for future conversations that it will take place. So going back to the presentation, so going back to the foundation of NLP from top to bottom, a text can be information can be extracted or just features can be extracted from texts on different levels, from a word level, from a phrase level, and from a paragraph level. From top to bottom, sound or words, these are or can be considered as the building block of natural language processing because it's the single unit that gets processed, or almost as if it is the atom. And it goes all the way to the discourse of the conversation, where the machine learning or the predictive model needs to understand the intention or the meaning of a text that needs to be interpreted and needs to be understood in a context. A couple core technologies that apply for these different levels can be seen as language modeling, part of speech tagging, syntactic parsing, word sense disambiguation, and sequence modeling. For the purpose of this research, we will be focusing a lot more on sequence modeling as it is considered to be a very robust technology to handle discourse and to be able to process discourse. These are only couple applications that we can derive from these technologies. Those can be information retrieval, information extraction, machine translation, question answering, sentiment analysis, and summarization. For the scope of this presentation, we are not going in detail about each of these applications, but we can intuitively and just by living these applications on our daily lives assume what they do on a higher level. So focusing on the sequence modeling and transduction, these technologies can have applications in speech recognition and machine learning. For example, understanding what I'm talking right now, that would be speech recognition, and the ability to translate from, for example, French to English or just any other language to English. That would be a machine translation application. And up to the point where this research was introduced, a lot of or state-of-the-art results were being achieved by the use of recurrent neural networks. More specifically, by applying long short-term memory (LSTMs), gated recurrent unit (GRU), and deep RNN. And this was achieved because it was able to create model dependencies along the input and output sequences. So we are not going in detail about the specifics of how RNN process the data and how the network gets to give a prediction, but just so we understand, depending on the size of the text, so if a text is really short, you don't require a lot of memory, you don't require a lot of dependencies in order to predict what is coming next. But if the text gets longer and longer, for you to be able to predict what's coming next, you need to consider the entire text as a dependency in some scenarios. And that creates a parallel processing constraint. Simply putting, because of this inherent sequential way that data gets processed, it's difficult to break the dependencies and process these dependencies in parallel. So only just an analogy, we would have to put all processes in one thread, putting in a very low level understanding of this. And to try to solve this issue, this paper make use of a previous research from 2017 in a collaboration between Google and the University of Toronto, where they introduced a transformer model that can be used in the unsupervised learning stage. And this is very powerful because it creates a model, it allows model dependencies without regard to the sequence size. So it tackles directly the issue of dealing with long-term memories or long-range memories. So as the text gets bigger, this new approach allows a better way of processing that kind of data. And this can be achieved by what they call attention mechanism. We will not go in detail about what it exactly is, but just keep in mind that it have achieved or that it have beaten former results made by RNN. And as a consequence, it allows a more efficient parallel processing. So the goal for this research is to explore a semi-supervised approach. By that, we mean that we're going to make use in the first stage of an unsupervised pre-training with the aforementioned technology or model transformer, and also make use of a supervised fine-tuning. So we will transfer the generated model from the unsupervised stage and apply that model or transfer that model into specific tasks that needs to be done in the NLP field. And all of these, it's done to allow a model to learn a universal representation. So basically, instead of having a plethora of models or a collection of models for individual tasks, right, that are optimized for individual tasks. The goal of this paper is to generate one single model that can embrace, that comprises, that it's able to handle different tasks in different contexts just as well as having all those collections. So the basic setup of the experiment to validate this model or this framework that was introduced by using transformer, this experiment made use of 7,000 unique unpublished books by a data set that was generated from a previous research from the University of Toronto. And they applied an unsupervised pre-training by the usage of the transformer to generate the language model or the predictive model off of these unlabeled data. And on top of that, they've transferred the language model to do a supervised fine-tuning on top of 4 tasks in NLP: natural language inference, question answering, sentence similarity, and classification. And each one of these tasks were given one or more data sets where the language model ran on top of it. So now going to almost the last stages of this presentation. This research was published at the OpenAI website. And if we have a quick look at it, we're going to be able to see a couple of the results that they have achieved. Let me just quickly, okay. So this is a summary of what the paper is, and this is where they published the paper, and the result as it is displayed, it's very prominent and very powerful because it beats 9 out of 12 previously set scores by former models, by individual models in each one of these data sets where the model ran. So how powerful this new model is by the usage of transformer and a fine-tuning supervised learning approach is that one single model is beating in 9 out of 12 previously set scores by individual models applied to each individual data set. So it's a very huge achievement that these researchers have achieved. So if I'm going to scroll at the very bottom just so we can see the type of data set, just a couple examples of data sets that the model needs to accurately predict. So for example, let's see, if you look at this table, you will be able to see the data set where the example belongs to. And on the right side, this data set has a label attached to it. So the machine learning or the language model is supposed to, by reading this example that belongs to the specific data set, it should output the same label to get an accurate prediction. So for the sake of this presentation, if we look at, for example, this race data set, it gives you an example of a huge text that tells you, I'm not going to go through the text, but we have to understand that it outputs a number 4. And by number 4, we have to interpret, the language model needs to interpret this text and gives back or output or predict that she had already known what was written in the letter. So it should be able to give an answer or a text interpretation off of a huge text. So if you look at this, this is a very huge, very good or very prominent achievement that this model gets. But it's not just being able to predict in a huge text, but it also is being able to outperform previous models in different tasks such as similarity as well. In this case, it looks at two sentences and it outputs or predicts whether they are the same or not the same, or if they have a similarity in it. And based off of that, the model gets a very high score in terms of its predictive accuracy. Oh. Okay. And also last year, researchers from also the University of Toronto have published a general language understanding evaluation, or GLUE benchmark, where all of those data sets that we talked about at the OpenAI website, it's also present at the GLUE benchmark website. So if you look at this really quick, we can see that there is a leaderboards ranking table, and by the time where this paper was introduced, the author Alec Radford from the University of Toronto, he must have been probably on the top 5 rank. But we can already see, and he got a 72.8 score percentage of accuracy, but we can already see that his score got beaten by other researchers or other models that were built, and we can put emphasis on Microsoft, deep neural networks example, and also Alice Large from Alibaba. So these are at the top 3 right now, and they have a really high score of more than 83%, or almost 84%. And that gives us a very understanding of, right? And they also have a GLUE human baseline, which I would assume that it was a score reached by a human, not by a computer. So computers are they are very close to the baseline set by a human. Right? So they would be able to, if they are already not, think as if they were humans. Right? So, yeah, going for the final conclusion here. This paper introduces a novel framework for strong NLU. Like we talk about the introduction of the transformer and also being able to fine-tune to specific tasks. That is considered the framework, and it allows a strong natural language understanding, or to be able to extract features off of texts. And as we saw, the model is task agnostic, at least up to the point where it does a generative pre-training. And it stops being task agnostic when we do a discriminated fine-tuning to optimize the language model to its specific tasks. But this model also had very good scores just by getting to the generative pre-training stage without the fine-tuning. So the greatest contribution of this paper, it's the combination of both. And it allows a significant world knowledge by the model. So the model gains a significant world knowledge by applying the transformer model. And it allows an ability to process long-range dependencies. So that goes in contrast with recurrent neural networks that it has limitation constraints or processing power constraints when it comes to large texts that inherently have lots of dependencies that needs to be taken into account. And with that, we conclude this presentation. Thank you.